Getting happier, I swear.
Happier, I promise. I promise. Who's ready to get really thrilled and happy? Let's get the best story. All right. Here's a story that sounds like science fiction, but it's very real science happening right now. Researchers have successfully simulated the entire brain of a fruit fly on a laptop. Every neuron, every connection, digitally mapped and recreated inside a computer. And the obvious question everyone is now asking, if we can do this with a fly, how long before someone tries it with a human? The project comes out of a massive international neuroscience effort that recently finished mapping the complete wiring diagram, what scientists call a connectome of the adult fruit fly brain. That brain contains roughly 139,000 neurons connected by about 50 million synapses, all reconstructed from microscopic imaging of the real brain. Once that wiring diagram existed, researchers took the next step. They built a computer model that recreates the entire neural circuit digitally. And here's where it gets real interesting. When scientists stimulated the simulated brain with inputs like signals representing taste or touch, the digital model predicted the exact neurons that would activate inside a real fly brain. In other words, the virtual brain began behaving like the biological one. Stimulate the taste sensors. The model predicted the neural cascade that makes a fly extend its feeding tube. Trigger sensory signals on the antennae. The simulation predicted the grooming behavior flies perform when something irritates them. The behavior wasn't manually programmed. It emerged from the wiring of the brain itself. That's the key idea behind the entire project. If you know how every neuron connects to every other neuron, you may be able to simulate the brain's behavior purely from its structure. Right now, let's be clear, this model is simplified. The researchers themselves describe it as a relatively basic computational version of neurons, ignoring many biological complexities like cell shape and chemical variations between neurons. But even with those simplifications, the model still predicts real neural activity surprisingly well. And that's what has neuroscientists excited, because the ultimate goal here isn't just digital flies. The next target scientists talk about is the mouse brain. And beyond that, the human brain. The reasoning is simple. If researchers can map and simulate the wiring of a brain, they could potentially study how neural circuits fail in disorders like epilepsy, depression, or neurodegenerative diseases by testing changes in the simulation instead of experimenting directly on humans. Or at least that's the beautiful package they sell it in. In theory, you could model a diseased brain, adjust the wiring, test drugs virtually, and predict outcomes before a real patient ever receives treatment. That's the optimistic vision. But here's another side to the conversation that people are starting to ask quietly. If you eventually simulate a brain with billions of neurons, and that brain processes information the same way a biological one does, at what point does the simulation stop being just a model and start being something closer to a digital mind? Now, we're not there yet, not even close. A fruit fly has around 100,000 neurons, and a human brain has around 86 billion. That's a leap in complexity that makes the fly brain look like a pocket calculator compared to a supercomputer. But history has a way of showing that once something becomes technically possible, even in a primitive form, the pace of progress tends to accelerate. So today, it's a simulated fly brain running on a laptop. Tomorrow, it might be a mouse brain running on a supercomputer. And someday, researchers openly speculate we might be able to build a complete computational model of the human brain. not just to understand disease, but to understand consciousness itself. And that raises a fascinating question for the future. If the brain is ultimately a network of signals and connections, is the mind something that requires biology? Or is it something that could exist anywhere with the right circuitry, even inside a machine? And that's the frontier of neuroscience. And we're slowly approaching its climax. So with that, I want to kind of flip it to, we have Dr. Alex Wissener-Gross, and he kind of presents the first multi-behavioral brain upload. This was his project, and he does it's dense. It's only a couple minutes. So I'm going to give my thoughts about you, the audience member, here in a minute, because I understand we shy from sophistication, but maybe instead of just leaving the world to be solved by great minds, you can hold yourself to a higher standard and try to become one. So I'm learning that, like, the second it becomes just a little weighty, people unplug. And I need you to know this is the future, and you either try to keep up with it or it's going to leave you behind. So without further ado, I'm going to flip it here to, again, Dr. Alex Wissener-Gross and his new great development.
Singularity has belonged exclusively to artificial minds until now. For decades, whole brain emulation has been the tantalizing counterpart to artificial intelligence. Copy a biological brain, neuron by neuron and synapse by synapse, and run it. Today, for the first time, I am releasing a video from a company I helped found, Eon Systems PBC, demonstrating what we believe is the world's first embodiment of a whole brain emulation that produces multiple behaviors. Watch the video here. In 2024, Eon's senior scientist Philip Hsu and collaborators published in Nature a computational model of the entire adult Drosophila melanogaster brain, containing more than 125,000 neurons and 50 million synaptic connections, built from the flywire connectome and machine learning predictions of neurotransmitter identity. That model predicted motor behavior at 95% accuracy, but it was disembodied, a brain without a body, activation without physics, motor outputs with nowhere to go. Now the brain has somewhere to go. Building on previous work, including Hsu et al.'s whole brain computational model, the NeuralMech-Fly V2 embodied simulation framework, and Ozdil et al.'s research on centralized brain networks underlying body part coordination, this demonstration integrates Eon's connectome-based brain emulation with a physics-simulated fly body in MuJoCo. The result: multiple distinct behaviors driven by the emulated brain's own circuit dynamics. Sensory input flows in, neural activity propagates through the complete connectome, motor commands flow out, and a physically simulated body executes the output, closing the loop from perception to action for the first time in a whole brain emulation. This is a qualitative threshold, not an incremental one. Prior work in this space has either modeled brains without bodies or animated bodies without brains. DeepMind and Genelia's recent MuJoCo Fly used reinforcement learning, not connectome-derived neural dynamics, to control a simulated body, C. Elegans, projects like OpenWorm, have attempted embodiment, but with far smaller nervous systems, approximately 302 neurons, and limited behavioral repertoires. No one has previously demonstrated a complete emulated brain derived from a biological connectome, driving a physically simulated body through multiple naturalistic behaviors. The implications cascade upward. Eon's mission is to produce the world's largest connectome and highest fidelity brain emulation, targeting a complete digital emulation of a mouse brain and laying the groundwork for eventual human-scale emulation. A mouse brain contains roughly 70 million neurons, 560 times the fly's count, and the team is currently amassing the connectomic and functional recording data needed to attempt it, combining expansion microscopic to map every neural connection with tens of thousands of hours of calcium and voltage imaging to capture how those networks activate in living tissue. If a fly brain can now close the sensoromotor loop in simulation, the question for the mouse becomes one of scale, not of kind.
Bringing it in here. Basically, what they did is run a simplified model to predict some neural activities in the fly's brain, not simulate the entire brain. So I just wanted to make that clarity, because what they're able to do here is create a digital simulated mind, and they haven't been able to enact it. Like, we don't have robot organic flies yet. So what they had to do was make a digital simulation that the robot could control. And they were able to show that at least this digital mind that they were able to map of a fly was able to work. I more than anything wanted to present this topic because there isn't much more to discuss beyond what it is. I do. Yeah, Ricky, let me get some thoughts from you.
Isn't this why Walt Disney froze his head? Isn't this
It is
why
exactly why. And it is funny that neurodevelopment, what was kind of like a laughable joke, is becoming more and more real. I mean, think about, wow, Ricky.
I only remember because Will said it like last week or something like that, right? And I was like,
and now you're seeing, wow, Ricky, you're seeing how it works. You know, when you're a child and you kind of get that like fantastical perception of like how it is, it's like, oh, well, they're going to get the technology to like Frankenstein his head onto a new body or back onto his body. But Ricky, you're pointing out a great reality of how this science is going to be applied. You're never bringing that organic head back to life. But what you'll redo is completely recreate the brain mapping that is frozen and saved. And so really, like the Futurama gimmick of like a head in a vat, you're never really going to see that. What you're going to see is like a version of Get Out, where I am recreating my entire mapped brain, and I can put myself in Brad Pitt's 25-year-old body. So now I look like Matthew McConaughey, and I'm still me. And it's not me, but that me is going to think like me, convince itself it's me, confidently feel like it's me, but does it have the same soul? And now we've opened Pandora's box.
At least he can say a smooth, all right.
Yeah, you never know. Put me in the right organic pod, and I might be able to. All right. You're closer to it with that cowboy hat than I am.
Go Buckeyes, bro.
Go Buckeyes. Dude, I got to tell you, the Buckeyes, they've been on a shit list this week. Talking about
Neuralink. So how you think this will, she just said it over here. How you think this will go with Neuralink too? Like, would they be able to, like from Black Mirror, would they be able to put our consciousness in the grain now and from downloaded from the map in our brain after we're gone for so long, mapping our brain, getting that map, putting that consciousness in the grain like they did in Black Mirror, and that subconsciousness can control our house. Oh my God. We're
well, and so you're seeing it isn't some like organic or like biological, what's the word I like? Yeah. It's not some tissue-based magic. It is a scientifically measurable map that once you completely develop and map its landscape, you're able to, okay, now not only can, like, let's say you have a map of the city of Cleveland. Not only can I recreate the whole same exact map, but now I can figure out ways to plug my map into a different map, Chicago's map. And so What is Neuralink? Neuralink is when part of that map is missing, we're filling in the hole. But then the scary part is that has its own connectability and, let's say, like wireless Bluetooth ability. And so who knows, down the line, this thing at its most, you could probably like change out consciousnesses where like that Neuralink is plug and playing, you know, taking from this map Ricky and putting you in Will's body type deal. Who knows? I really do hope God blows this whole thing up and the Antichrist goes to war before we really get this thing at its final stage. Because I don't need to see where this totally leads to. I've seen enough as it is. You would think babies on trains would be enough, but we're like, no, we need to make robot brains. And let's be real. This started with a fly and they're eager to jump on mice. That's going to happen so much quicker than we're willing to admit. I mean, it is crazy to think maybe about a year ago now, we were talking about the remote control cockroach where they put a chip in a cockroach's brain and they're just like, watch this. And it's like the chum bucket just that was not far down the line, and we've buried that. Now the cockroach is in my Grand Theft Auto, and I got him stealing a Lamborghini. Welcome to the future. Will, you could plug into a world to be with the burnt peanut.
That sounds great. I think I might pass on that. I think I might pass. I think I get lost in there.
Fair. This one has been a doozy of an episode. We have just touched across all the landscapes of insanity. But let's do it as we always do. There's no better nightcap to our show than going to the Wheel of Topics. Will,